Okay, so the next setup that we are going to present uh, is a setup that will allow us to extract uh, all the small signal parameters from a transistor. So previously we have to set VGS and VDS, but that is not really very useful because we don't have a control of the current that we want to pass on this transistor. There is a very simple setup that allows to do that, and it is the following that we see here. So it consists of the transistor under test, which is basically size with variables, and then we have a current that also it is dimension with the variable. This current it is going to be connected to the drain. Okay, and next we have voltage source. This is source, and this one it's connected to a voltage control voltage source. So how does it work? This works pretty much similar to op amp. Okay, it has a very large gain, this, and the output of this very large gain amplifier, it is going to be connected to the gate of the transistor. Remember that this transistor that it is now connected as a common source amplifier will have a signal inversion from the gate to the drain, meaning that this system has a negative feedback. Okay, so it is a negative feedback system. So what is going to happen in this negative feedback system is that the gate voltage that this amplifier will set will guarantee that this drain to source voltage in one terminal will be the same as the voltage at the drain. So basically the feedback it is going to force these two voltages to be the same, the drain voltage and the VDS voltage. And for that to happen, all the current that it is in this DC current source must be sunk by the transistor. So there is no way that this current goes to the right because this is a voltage control voltage source, is infinite impedance. So all the current has to go directly to the transistor, to the drain of the transistor. So this negative feedback system will place this transistor in the right operating region for a particular drain to source current and a particular drain to source voltage. So let's save this schematic, and then we are going to use the simple ADE, okay, that we have studied before to set up the simulation. So very often for very simple setups the ADE it is more than enough. We only need to go to the ADXL or ADXL if we need to do rather complicated simulation setups. So we can put, for instance, 10 microamps, the length 180 nanometer, and number of fingers 1. PDS we can put 0.9 volts, and the width per finger we can put 8 micrometer. We set up the DC operating point as we did before, and we are settled. We send it to simulation, and actually, yeah, we can send the simulation as we did here and plot the results, but the ADE also has, when we open the ADE, has placed this toolbar here that is also very useful because we can run actually the simulation from here. So we're going to do it from here now. We run the simulation, and yeah, we check that it was successful. We check the log, no problems, and then we can annotate the DC node voltages, and then we see something very nice. The feedback system, it is working. It has placed 347 millivolts at the gate, and let's see the current if it is. Yeah, so there is 10 microamps of current being sunk in this transistor, and those ones come directly from this current source. And the drain has been placed at 900.3 millivolts, so which it is exactly what we wanted. Now I have already shown you before the results. The DC operating point are in the browser, so we can open the browser, and then we go to the DC operating point. It will be DC op info M0, M1, and then we got basically everything that we need. So there is the drain current, there is ID located here, there is GM, there is GDS, it is basically everything that it is needed. Well, so we can do exactly the same as we did before. We're not going to do it now. We already showed that. What we're going to do is we are going to create a script here. So we're going to save this one, and then we're going to write it out self MOS, and then write it EL, and then okay. Then now we just created this one. Then we can just bring it here. So it was called self-MOS. Okay. And I will open it with the skill IDE. So we have it in scripts day 2 on, it was called self-MOS. Yes, self-MOS, and here is for simulation setup. Now I'm going to show you some other things that might be useful. So in this case, the netlist, it is going to be taken from this line, but I might as well create a netlist with the following command if I want to. And I can actually tell the script where to find the design for creating a netlist. It will be like this. It will be design, the name of the library, that it is day 2. It is the name of the cell. The cell, it is a self and MOS, and the kind of cell, it is a schematic circuit. So with this one, With these two lines, the Cadence will know where to search for the schematic and create a netlist with this one. Okay, let's test if it works. I don't need anymore the IDE. Let's save the state anyway. We save the state in the cell view. Okay, and then we just close it. And now we are going to run this. Control L, Control Lima, then we run and it is successful. Okay. Good. Now something else that I can do is to pick up the values of the transistor, the size of the transistor, and the current and VDS from another script. Then I can reuse this line. I come here and yeah, I can actually put it just before the analysis. This one, and then when I include this file, then I can replace this one with the values of the variables that are in the file. That will be these ones. Something important, the best it is not to mix the names of the local variables that I have here in this file, not to have the same as the variables that I have in the schematic, because that will cause problems later. VDS1, and then we have WF1. Okay, and that is it. And now I need to get the capacitors, the current, and everything that I need. But we already know how to do that. I just checked that the name of the transistor is the same. This is M0, so that is correct. It is going to search for M0 and M1. Yep. So we are basically settled with this. I think there might be that we need drain to source capacitance and drain to bulk capacitance also, so I'm going to also bring those ones. Drain to source capacitance here, so it will be drain to source capacitance and drain to bulk capacitance also. Drain to bulk capacitance, and that's it. I have everything that I need. If I want to calculate the intrinsic gain, I will need to multiply. I need to calculate the RDS. We do exactly as we did before. RDS equal 1 divided by GDS. And we are going to calculate the intrinsic gain. Intrinsic gain is transconductance multiplied by the output resistance. We are going to calculate the intrinsic, the transconductance versus ID, GMID will be ID, and then the FT of the transistor, that will be GM divided by 2 times pi, CGS, CGD, CGB, and this will be this will move the capacitors to femtofaraday, and divided it will be the frequency in megahertz. Yeah, so I think we are yeah, we have everything that we need. We need to print this information. So we can use the printing function here, and I prepare something from another script. So basically we need to change this is correct, this is correct, this is correct. We need to extract BGS also, that we can extract. It will be from here. Let's see. BGS. And I think now we have everything. So we have L1 that is in the script, in the global script. This is in the global script, global script, global script, and this is BGS. Then we have this is the total size, and that is correct. This is GM, RDS, CGS, CGB, and CGE. CDS, CDB, and BGS1, and G1, that it is the gain. Here it is the GMID, and this is FT in lowercase, and then save it. Let's see if we didn't make any mistake in this script. And there is something. Legal 4 per spec. Let's see what can be wrong in this one. Let's see, restart. Okay, that is correct. Okay, now we got it right. But this FT looks very funny, but we're going to fix it now. Okay, that it is unnecessary here. now it is fine. So the capacitors have disappeared here because we have put this value 4.2. So what we can do it is multiply everything, all the capacitors by 1x15, and then we get them. We get them basically in femtofarads, but then we will have to fix this one here down. So that will be x15 to bring it down to Faraday. Okay. Now, okay, now we got it right. Now, capacitors are in femto, and then we got the transit frequency GM over ID. Good. So this very simple setup allows us to get automatically information from the transistor. And now if I want to change the transistor size or change the current, I just go here, and for instance, instead of 10 micro, I try to test 1 micro, then I go 1 micro here, run the script, Control L, Control Lima, so then we get here for 1 micro up current we have the following FT, GMRID, and then the intrinsic gain, etc. Oh, there is something very funny here, BGS1. There is a bug, this shouldn't be multiplied by anything. Okay. Yes, now it looks like it is correct. Okay, something else that I can do is sometimes I update the design kit and the models change, and then instead of generating another script, what I can do it is just put the models in another file, and this is what I have it here. I have the models, the latest models that I download, they are these ones. So instead of using this, I can delete, and then I can load the models here. Actually, I can put the models first, as it was before, and then this will also work for me. So I hope you get the idea now that scripting, it has very interesting opportunities now. Changing the schematic, running the simulation, and getting this piece of information is possible using the graphic user interface, but it is no way that you can do it faster than just changing this one like this, and then just saving, coming back and running it. That is much more faster, and just to get this information very quick. So sometimes you need it very quick, and then that is the way.